So let's begin. So, good afternoon. My name is Rachit Verma. I am a PhD student in IIT Dharwad, and I have been assigned to hold problem-solving sessions for the course Foundations of Cloud IoT Edge ML. The professor assigned to this course is Dr. Rajiv Mishra, and this is problem-solving session of week 6. So before we begin with the session, I will go over how I intend to conduct this session. First, I will go over a summary of whatever was discussed in this week's lectures, and then after that, I have prepared I've prepared some questions, or some questions have been prepared by Rajneesh Verma and Shweta Verma with the help of some AI tools like ChatGPT, and we'll be discussing those questions, um, and then hopefully these questions will be of use for you to solve the assignments. Okay. So in week 6, so the first lecture was on mathematical formulations of task offloading in Edge Cloud. So we first discussed simple Edge Cloud system architecture, and we discussed some latency models, and that uh, that showed the impact of different tasks and offloading scenarios for time sensitive applications. And then we evaluated the latency models. uh, the, these latency models considered computation and communication as some parameters when they were considering offloading. So simple system architecture was discussed. So some a three-tiered architecture was seen over here. A simple three-tier architecture was seen over here, and we saw we saw what the edge controller layer. We saw the edge controller layer, and we saw where it is placed in relation with the cloud and the edge, and we saw its various components such as the application manager, the infrastructure manager, the and the planner and the planner. We discussed some latency sensitive applications, and we discussed a simple latency model, and after that we discussed a simple formulation over here. Then some simulation experiments were discussed and their results. And then after that, in the second lecture, we discussed how task offloading could be performed with the help of LSTM and with the help of deep reinforcement learning. And we discussed the initial simple architecture of an edge computing system with a mobile device and edge node. So we discussed what the kinds of queues that would be inside the mobile device and the edge node, and how they would assist in offloading. And over here we discussed a simple task model. We saw that a new task generated by the terminal device is denoted as having as containing information pertaining to the size of the task data, the computational resources required per bit, and the maximum tolerated delay of the task. And then we saw a simple decision model over here, which would then be used for offloading. Saw some simple equations, and then after that we then gave an overview of the task prediction model. And then after that we discussed how the deep reinforcement learning agent and the LSTM network, how these two would come into play in order to conduct offloading. And then we saw the double DQN model, and then after that saw a simple numerical. Then we discussed what vertical and horizontal offloading was, and in the vertical and horizontal offloading context. Just a second. We saw a simple architecture in which it was relevant. We saw each of the tiers in the vertical and horizontal offloading context, and we saw some. Then after that we saw a basic. We saw how this could be formally represented in terms of its various components and some symbols. how this could be formally represented basically. And then we discussed how the total cost of a cloud edge computing environment could be calculated. We saw that it could be calculated in the form of the computation cost and the communication cost. And then we then discussed very briefly that uh, this kind of this kind of problem this kind of problem could be solved with a branch and bound problem, with a branch and bound algorithm. We saw some experiments in some scenarios. And then we then went on to the global state and snapshot recording algorithm. We first saw the problems with we saw why recording the global state is actually a very challenging problem, and it is not trivial. We saw a simple example. We saw a system model over here, and we saw a simple system model of um, we saw a simple system model of how a number of processes communicate with each other. And we discussed what it means to have a consistent global state and an inconsistent global state. And then finally we saw the we this was then made clear with the help of a money transfer example. And then we saw the Chandy Lampert snapshot algorithm. Okay, fine. So then let's go on to discuss the questions.
I have a question
Okay.
regarding. So, can you go back to that penultimate slide where the green marker is there, green colored banking? Yeah.
Yeah.
Say in time, say just after the marker happened at B server,
Okay.
there was another transaction that happened, say any number 2050 from B to A.
Huh. Okay.
Okay, actually we have assumed C4, so okay, I got
Okay, fine.
C4 model as it's okay, fine.
Okay, fine. No problem. You can send me an email also.
I also had another doubt regarding that batch size numerical.
Batch size. Okay, sure. I'll just get to it.
Where those epoch and everything was.
Yeah. In the lecture 13, right? I think. Okay. I mean
Yeah.
LSTM lecture, I think.
Yeah.
Fine. Just 1 minute. Right.
Yeah, this one. So, I'm not getting this into 64 multiple actually. If you see, total data points is 7,000. We have. Can you go back to the?
Yes. This here.
Yeah. This slide. Number of data points is 7,000, and the batch size is 64. Total number of batches is 109, and we are saying there are 50 epochs. So total batches process will be 50 into 109 into 5. So why is that 64 again coming into picture?
Oh, here, this one.
Yeah.
Okay.
See, total data points is 7,000. Batch size is 64. So if I divide by that, 109 is the number of batches.
Yeah, you get 109 batches, correct?
And there are 50 epochs. So 50 into 109 is the number of batches actually processed.
Yes.
And each batch processing requires 5 seconds. So it should be 50 into 109 into 5. Why is that again that 64 multiple coming?
Okay, you are right. I mean, so yeah, so the number of okay, wait. Let me just take a look. So number of epochs into number of iterations per epoch. Okay, 50 into 109. This is correct.
This is correct.
Time taken to process one batch of data on a GPU is 5 seconds. Fine. This is also okay. Fine. So 50 into 109 would be how many batches? Into 5 would be the
answer.
Yeah. So Mm-hmm. Okay, okay. Yes, that might be a mistake. Okay, I will. Is it fine if I get back to you?
Yeah. Mm.
So definitely the 64. Yeah, so that's already been considered, right? Over
Yeah.
here.
5 considers the
Yeah,
5
and this
seconds.
is yeah, this has already been considered here, and this is uh, 5 seconds per 5 seconds per 64 units
Yeah.
basically.
Mm.
Fine. Okay, 5 seconds per 64, and okay, I will. If it's fine with you, if I'll just get back. Can you drop your email or something over here, or can you just send me an email, like on,
Yeah, I'll drop it once.
or you can send me an email on.
Okay. Okay, fine.
Okay, so let's begin with lecture 12. Okay, so wait, just 1 minute. So let's start. See, so I generally start with these generic questions first, because if there are new people, because this video will be uploaded to YouTube, and if there are any new students, they should be able to benefit from these generic questions as well. So, what term is used to describe the connection of numerous devices directly to the internet, as mentioned in the text? Is it A, Internet of Computers; B, Internet of Things; C, Cloud Computing; D, Edge Computing? I mean, answers there, but anyway. So, anyway, the answer is Internet of Things, IoT. Okay. Uh, let's go to the next question. So, what concept is described in the text where mobile devices offload heavy computation and storage tasks to resource rich nodes in collaborative edge or cloud environments? Is it A, task switching; B, cloud computing; C, task offloading; or D, edge synchronization? So, so Dev says C. Any other responses? Okay, okay, so the answer is C. Okay, the answer is C, task offloading, and the other task switching and edge synchronization, they're not relevant over here. And cloud computing is a very generic term. Okay, fine. So the next question is, what is the purpose of task offloading in the context of IoT devices? Is it A, to increase the number of tasks performed on the device? Is it B, to decrease the reliance on edge and cloud resources? Is C, to enhance customer experience and accelerate job execution? Or D, to limit the capabilities of mobile devices?
E.
Okay, yeah. So the answer is C, to enhance customer experience and accelerate job execution. And the other question, A, to increase the number of tasks performed on the device. Well, um, I wouldn't say that's actually directly true. We want to make sure the tasks happen much faster. Um, we don't really care if one device is performing more tasks. We only care so much. We only care enough so that all the tasks that actually happen, they happen as fast as possible. And so now, as far as the reliance on edge and cloud resources is concerned, So we we don't we may want to reduce the reliance on one of these individually and increase it on one more depending on the situation, right? So uh, so in the end, what we actually want to do is we want to make sure that the reliance on the mobile device or the end device is actually reduces. Okay, and D is obviously wrong. We don't want to limit it exactly. We want to maybe reduce reliance. Okay. So in the collaborative cloud edge mobile model described, what are the resource rich nodes referred to? Is it A, IoT devices, B, mobile devices, C, edge and cloud environment, or D, resource poor nodes? The resource rich nodes?
C.
C, yeah. Okay. So they have said A. So the IoT devices aren't exactly resource rich, but in comparison to the IoT devices and the mobile devices that are at the bottom tier, the edge and cloud, sorry, the edge and cloud. You're
I
saying?
was about to say C, sir.
Okay, fine, fine. No problem. So the edge and cloud environment have much richer resources in comparison to the IoT devices. Okay. So so which type of tasks are typically offloaded by mobile devices in the context of task offloading? Is it A, light computation tasks, B, storage intensive tasks, C, communication tasks, or D, compute heavy or storage heavy tasks? So,
D.
D. Any other responses? So, which type of tasks are typically offloaded by mobile devices in the context of task offloading? Light computation, storage intensive, communication task, or compute heavy? Okay, fine. So the answer is D, compute heavy or storage tasks. Okay. So now why compute heavy or storage tasks? Because as we just discussed, the IoT devices are not very do not have sufficient resources to do this kind of compute heavy or storage tasks. So they need to be offloaded with the help of some sort of deep reinforcement learning, or with the help of some sort of policy. Okay, light computation tasks need not be. Storage intensive tasks may you may need to offload, but of course it is not as all encompassing as option D. So yeah. So what is the primary challenge in resource management within the edge cloud environment as mentioned in the text? Is it A, connectivity issues, B, heterogeneity of resources, C, lack of IoT devices, or D, limited cloud storage? So you can see this multi-correct also, but I mean single correct would be I think more appropriate. Okay, Dev has said B. Any other responses?
B, sir.
B? Okay. Fine. Heterogeneity of resources. So yes, so what is this heterogeneity of resources? So in the edge, right, all the devices that are deployed on the edge layer may have different CPU powers, may have different GPU utilization power, may have GPU speed or CPU speed, or they may have different storage capacities. So accordingly, the edge So accordingly, the edge orchestrator or the edge layer has to make sure that the tasks are offloaded appropriately. So that is why. So that is what the heterogeneity of resources kind of implies. So which factor makes resource management uh, in the edge cloud environment crucial for supporting IoT applications? Is it A, decreased number of IoT devices, B, improved network speed, C, enhanced user experience and performance, or D, reduced application complexity? Any responses? Okay, Dev has said C. So yes, so C is the correct answer. Um, so decreased number of IoT devices. It's not necessarily true. There are an n number of IoT devices on the bottom tier, and why is it crucial, right? So when we're looking for something negative when we want to figure out if something is crucial or not. So improved network speed is not really a negative aspect of the environment that is leading us to make the edge cloud environment crucial, right? So enhance user experience and performance. So that is uh, so even the improved and also like in the improved network speed, right? You know, to some extent you could actually say that it is the right answer, um, because I apologize. It would be more appropriate to talk about the network in terms of bandwidth. Okay, for the second question. So if you look at 2C, like 2C is the right answer over here, because like it's kind of all encompassing. Uh, so we want to make sure that resource management in the edge cloud environment is happens, so that user experience and performance can be dealt with. Okay, so two answer is C. So for the third one, what impacts the end-to-end service time and performance of IoT applications in the edge cloud environment? So is it A, different offloading strategies, B, uniform resource distribution, C, reduced network latency, or D, simplified application architecture? So can you answer this question in the sorry? Can you answer this question in the context of what has been like taught to you in the course, if possible? Okay, Dev has said A. So yes, so different offloading strategies can definitely impact the end-to-end service time and performance. Yes, so network latency can also impact the end-to-end service time. Mhm. So I mean, primarily, if you look at what has been taught, like A and C has been taught to you, but if you look at hello, yes, do you have okay? So if you look at what has been taught to you, A and C would be the most appropriate answers. So if the offloading strategy is optimal, then you'll have good performance in the IoT application, and if your application architecture is simplified. So for example, if let's say your if let's say your architecture does not have that many components, right? Then also you may uh, then also you may achieve a good amount of performance. So, but D is still somewhat vague, right? Because even if the architecture is simple, if there may be bottlenecks in the architecture. So, and also as far as uniform resource distribution is concerned, that might make it easier for the offloading policy to choose an appropriate device or something like that. But still, even if the resources are uniform, some may be some may be less powerful, some may be more powerful. I mean, if all of them are, let's say, less powerful, right, you will still have like low performance. So so A and C would be the most appropriate answers. A and C. Okay. Fine. So why is offloading IoT tasks to resource? Okay, let's skip this. But it's the same thing. So what is the primary objective of scheduling offloading tasks in Edge IoT system architecture? Is it A, to maximize the amount of data transmitted in the network? B, to minimize the offloading latency? C, to increase the computational demand on IoT devices? Or D, to reduce the resource richness of the edge and cloud systems? Shweta Verma has said A. Okay, I think that was for the previous question. Okay. What is the primary objective of scheduling offloading tasks in Edge IoT system architecture? Is it A, to maximize the amount of data transmitted in the network, minimize the offloading latency, to increase the computational demand on IoT devices, or D, to reduce the resource richness of edge and cloud systems? Okay, so so B is the answer, to minimize the offloading latency. So this would be the latency incurred as a consequence of offloading, right? So for example, if you have a task and you want to offload it, there is some you have to spend some time transferring the data corresponding to the task to the, let's say, from the edge to the cloud, and after that, after the cloud actually processes the task, it will give some response. So there's some time corresponding to that. So you want to minimize this time, and so you have to make sure you choose the right edge node, and you have to make sure you choose the right you have to make sure you only offload to the cloud when really necessary. And to maximize the amount of data transmitted in the network, that's not true. In ideal situations, we want to minimize the amount of data transmitted to increase the computational demand on IoT devices. That is a negative thing. Generally, we want to decrease it as a consequence of offloading, to reduce the resource richness of edge and cloud system. That would also be very negative. We don't want to do that. So this is also pretty straightforward, but what do offloading latency models investigate in the edge IoT system architecture? Is it A, the impact of different offloading scenarios on network latency? B, the computational complexity of IoT applications? C, the demand for computational and communication resources? Or D, the effect of edge and cloud resources on IoT device performance? They have said A. Yes, so A is a good answer. Any other responses? 3D. Mm-hmm. So, okay, so I see there's some amount of confusion between A and D. Okay, so the answer to question 3 is A actually. Okay, so now why is that, right? So why is D not an appropriate answer? So we want to figure out not the performance of one individual device exactly, right, or an individual layer. We want to see how the entire system is performing. So that is captured in the first option, um, on network latency. So as far as that is the main difference between like A and D. We don't want to know how exactly like one device is performing. We want to see if the end device is being is receiving its response on time, right? So that is kind of obtained that is obtained from understanding how like the entire system is working. So, and also the IoT device is what you will be taking tasks from, right, and actually taking tasks from and actually executing them. So like the IoT device, you could say, is kind of like the client in the end. You don't exactly in these kind of tasks, you don't exactly measure the performance of the IoT device. So, and also as far as B and C are concerned, they're kind of they may indirectly play a role, right? But we don't exactly investigate them. They may indirectly play a role in figuring out if your offloading scenario is performing well or not. But we don't investigate them. We may use this kind of this data in some way. So in the architecture of edge IoT systems, what comprises the bottom layer, tier 1? Is it cloud servers, IoT devices, augmented reality headsets, or edge servers?
PNC.
Okay, so yeah, you could consider augmented reality headsets as IoT devices. It won't be wrong, but generally it's not there in every kind of architecture, right? So if you ask me, in my opinion, it would be more accurate to say just B. Okay, IoT devices. So what is the primary characteristic of devices found in the uh, bottom layer of the edge IoT architecture? So is it A, they are primarily stationary, B, they are connected to the cloud only, C, they are resource rich, or D, they run different applications? So Dev, is that answer for 2? Okay, D, they run different applications. Any other responses? A, C, and D. So when Indra has said A, C, and D, so no, let's think about this carefully, right? So what is at the bottom layer of the edge IoT architecture? IoT devices. So our IoT devices is always stationary. Okay. So can IoT devices primarily stationary? So let's think about. So if you have a car, right? A car can also be an IoT device. So not only that, if you not only a car. Like let's say you have a smartwatch, and you are moving, right? So and then your smartwatch is also not stationary. So as far as see they being resource rich, that's not necessarily true, because IoT devices may be something like a toaster or something like your something like a smartwatch. So in comparison to something like your smartphone or your computer, they don't have the same amount of CPU or CPU or memory or something like that. So they may not always be that resource rich. But as far as D is concerned, yes, they can run different applications. For example, a smartwatch, let's say, a smartwatch may have a heartbeat tracker, may have a pulse monitor, or it may have also, and it also tells you the time. It can also tells you, and it also, let's say, can pick up your calls, and you can write emails through it. So that you will find in several applications. And even if you, and many times you'll see these sensors in IoT devices, right? They are kind of attached to like a microcontroller. So their entire so that entire board you will see is may run like several applications simultaneously. Let's do this quickly. Which of the following is an example of an IoT device found in the bottom layer? So is it cloud server, smart refrigerator, mainframe computer, desktop PC? It's a smart refrigerator. Okay. The others are like are resource rich, right? You'll find smart refrigerators offloading their tasks to these devices. What is another term used to refer to the edge controller in the edge cloud system architecture? Is it A, cloud node? Is it A, cloud node, B, edge orchestrator, C, end user device, or D, cloud controller? Panindra has said B. AV Panindra has said B. Any other responses? B. Okay. Yeah, so this is also simple, less direct. So if you have listened to what Sir said, so the edge controller is also called the edge orchestrator. Yes, you are correct. So what are the functions of the edge controller in the edge cloud system? Is it A, collecting status of resources in the system, B, managing application services in the cloud, C, deploying IoT devices, or D, managing communication between end user devices? So they have said B. Any other responses? Mm-hmm. So,
A.
sorry, A?
A.
A is also A is correct. B is also correct. Any other responses? Okay, fine. So yes, so the answer is A and B. So we know collecting status of the resources in the system, that is handled by the infrastructure manager, and B, managing application services is done by the application manager. Deploying IoT devices, so that is not true, because we assume that the IoT devices have already been deployed in the system before we go for the edge controller. And managing communication between end user devices, that has not been discussed, at least. This is kind of primarily responsible for handling the edge and the cloud, those kind of transactions or resource management or whatever. End user devices that's not handled by the edge controller. So what are the components of the edge controller responsible for managing the edge cloud system? Is it A, application manager, B, infrastructure manager? Oh, sorry, is it A, application manager, infrastructure manager, monitoring and planner, B, cloud server, edge node and end user device, C, router, switch, firewall, or D, database server, web server, application server? Yes, so Panindra said A. Yes, this is also a simple question. So this is pretty direct, straightforward from the text. So let's take a look at your notes over here. So it contains four things: application manager, infrastructure manager, monitoring, and the planner. Okay, fine. Let's go to the next one. The other are they're too general or they're too specific. So where can the edge controller be deployed within the edge cloud architecture? Is it A, only within the cloud layer, B, anywhere between the edge and the cloud layers, C, only within the edge layer, or D, within the IoT devices? Yes, so what's the answer to this question? Okay, Dev has said B. Any other responses? C, only within the edge layer. That's not true. So as you may remember, so the edge controller is responsible for for managing application services. So application services infrastructure. So it can be deployed anywhere between the edge and the cloud layers. Okay, so within the edge layer you will have like all the edge devices and all that, but the component that is responsible for managing these edge devices will be like external to it most of the time. There can be some kind of internal thing also, but it makes more sense to keep the component that is responsible for managing the resources and everything external to it. So since the edge controller does exactly this, it is between the edge and the cloud layers, and of course it need not be within the cloud layer because then it may be a little bit harder to manage, because once again you'll have a huge amount of latency in giving the decisions to the edge. So we want to make sure it is at least somewhat close to the edge. We want to make sure the edge controller is at least somewhat close to the edge. Okay, and within the IoT devices obviously, because one thing is the IoT devices won't even be able to do the kind of won't even be able to do the kind of like intense computation that may be required of the edge controller, because they're low resource. So what is one of the primary roles of the edge of the edge controller in the edge cloud system architecture? So is it A, managing end user devices, B, providing resources to IoT devices, C, synchronizing data with end user devices, or D, scheduling offloading tasks to satisfy application users? AV Panindra has said D. Any other responses? Okay, Amit Sharma has said D. Yeah, so definitely D is the correct answer. So scheduling offloading tasks to satisfy application users, that is one of its primary tasks. Synchronizing data with end user devices, not necessarily true. We generally, I mean, we have only studied like synchronization of time. Uh, but this is, even if it is true, it is not really a major one of its major roles. Providing resources to IoT devices, it does not exactly provide resources to it. Like tasks are offloaded to the edge with the help of the edge controller. So the resources of the IoT devices are not augmented in any way. A is also wrong because the edge controller is primarily for edge devices. So what is the primary responsibility of the application manager in the edge cloud system architecture? Is it A, managing physical resources, allocating virtual machines, managing applications running in the edge cloud system, or D, collecting information about connected IoT devices? No, the edge controller and scheduler is not exactly the same. Even though the edge controller does scheduling, like the policy part of the policy component, sorry, the planning component of the edge controller does scheduling, but it is but that is not its entire role. Okay. I hope that is clear. So what is the primary response? Okay, they have said C, managing applications running in the edge cloud system. So okay, actually, let's look at this question a little bit more in detail. Is edge controller and scheduler the same? So if you look at the components of this, right? So the edge controller kind of handles it manages application running in edge cloud system. So this includes like amount of data to be transferred, amount of computation requirement, latency constraints. So now you could say to some extent like scheduling is happening, but still like there's a lot more, right? So it is in charge of the physical resources. So and then as far as the infrastructure manager is concerned, it monitors application tasks, so computation delay, communication delay, and but over here if you look at the planner, so the planner here is doing all the scheduling in the offloading tasks. So if this is what you meant, then like the planning part is being handled by the edge controller. Okay. Fine. So the answer is C. So we just this anyway. What information does the infrastructure manager collect and manage in the edge cloud system? Is it A, application tasks and requirements, B, number of application users, C, physical resources of the edge cloud system, D, latency constraints? I mean the most appropriate answer. Latency constraints. So is it just the latency constraints? if you look at your notes, right, so it does monitor application tasks, definitely, and during the execution of application tasks, and detects the task failures. And then, other than that, it is in charge of the physical resources in the entire edge cloud. So, in addition to the physical resources in the edge cloud system, it is also responsible for monitoring application tasks. Okay, and the relevant computational resources that are relevant to it. So, in a way, you could say it is answer two is application tasks and requirements, and C physical resources. Like both 2A and C would be correct if you look at the notes. Okay. Well, I would say like this requirements is not exactly mentioned in the text, but you could somewhat imply this, right? Because they do somewhat discuss that there's the computational delay and the communication delay. So these are indirectly you could say these are like the requirements. If these requirements are not being met, right, we need to like that's what it tries to figure out. So indirectly it is kind of looking at requirements as well, but definitely it is also looking at the physical resources. So you could say 2A and C are the right answer. So so what is the main role of the planner component in the edge cloud system architecture? Right? Is it A, managing physical resources, B, proposing scheduling? Oh no, no. What is the main role of the planner component in the edge cloud system? Is it A, managing physical resources, B, proposing scheduling policies for offloading tasks, C, managing applications running in the edge cloud system, or D, collecting information about connected IoT devices? So does the planner component uh, collect information? A.V. Panindra has said scheduling policy. Okay, yes. So if you look at your notes, as we just saw, the answer is B, proposing scheduling policies for offloading tasks, and it does not manage applications exactly. That may be kind of indirect, but like B would be the most appropriate answer. Let's take a look at your notes again. Right. So scheduling policy of the offloading tasks and the location where they will be placed. Right. So this offloading task works on this component and it passes its result to EC for execution. And okay. So how are latency sensitive applications supported in the edge cloud system? Is it A, by connecting to distant cloud servers, B, by deploying edge nodes close to the devices, C, by increasing the network latency, or D, by reducing the number of connected devices? Amit Sharma has said B. Any other responses? Okay, fine. So the answer is B, of course. We have seen this numerous times in the in the text. So if you bring edge nodes close to the IoT devices, you will see that you won't have to send data over a long distance, and so that will help latency sensitive applications. So what role do fog nodes play in the edge cloud system architecture? Is it A, managing physical resources, B, supporting latency sensitive applications, C, collecting information about connected IoT devices, or D, proposing scheduling policies for offloading tasks? B and D. So do fog nodes themselves propose scheduling policies, or is it like the edge controller that is proposing the scheduling policy? Okay, Amit Sharma has said B. So okay, so yes, so the answer is uh, so the answer is B. So much like edge nodes, even like fog nodes actually support latency sensitive application. Scheduling policies are not proposed by fog nodes themselves. They generally receive this decision from some external entity. Okay, this is also very simple. Let's just finish this quickly. What characterizes latency sensitive applications? Is it A, they require high computational resources, they have low sensitivities to delay in communication, they have high sensitivity to delay in communication, or D, they rely on cloud servers for computation? Yeah, they have high sensitivity to delays in communication or computation. B is the exact opposite of this, and resources does not have any computation resources does not have anything to do with latency. And yeah, they rely on cloud servers. That's not necessary too. They can rely on edge servers also for computation. So which of these scenarios exemplifies a latency sensitive application? Sending non-urgent emails, streaming pre-recorded videos, processing real-time data from self-driving cars, car cameras, or B, updating social media posts? C. Okay, that is correct. The others are streaming pre-recorded videos. So it is somewhat latency sensitive, but it is definitely not as latency sensitive as real-time data from a self-driving car camera, because the possibility of injury or death is there if you, let's say, encounter some accidents. So C is definitely the right answer. Sending non-urgent emails is of course, in its name it is not, by virtue of its name as being non-urgent, it is obvious that it is not latency sensitive. Updating social media posts also not necessarily. You can wait a little bit. Nothing urgent will happen most of the time. So what are the two key activities important in supporting latency sensitive application in the edge cloud system? So we have an equation that was discussed in this context. So anyway, is it application management resource allocation? Is it B, communication latency and computational latency. Uh, is it C, cloud server deployment and data storage, or D, IoT device connectivity and network security? A.V. Panindra has said B. Dev has also said B. Amit Sharma has also said B. Okay, so everyone is concurring at B. Fine. Any other responses? Okay, yeah, so the answer is B. Okay. Communication latency and computational latency. So one thing is application management, resource allocation. These are indirect. They indirectly feed into some either computation or communication latency. What are these, right? Computational latency is the amount of time it may take to like do some amount of like computation. But communication latency, on the other hand, would be how much time it may take to actually communicate the results of the computation. Both of these put together will impact the latency of your application. So C and D also indirectly may impact these two parameters. So, but if you want to see directly, right, what are the two key activities, it is B. So of course this question is directly follows from the previous one. What is the main priority in reducing latencies for latency sensitive applications? Is it A, reducing computational workload, B, minimizing delays in communication and computation, C, maximizing cloud server deployment, or D, increasing IoT device connectivity? Yeah, so it's B. It follows from the previous question, okay? Okay, let's skip this one. So what is the purpose of offloading low priority applications to the edge cloud system? Is it A, to reduce computational workload on IoT devices, B, to maximize communication latency, C, to prioritize rich customer experience applications, or D, to minimize cloud server deployment? Okay, let's go to the next lecture after this. Okay, so 3 can have various answers. Okay, A is also a valid answer, definitely, to reduce the computational workload on IoT devices, and C is also to prioritize rich customer experience applications. For example, if you're playing a game, right, and you want to, it may not be as high priority, but maybe your mobile phone may not be able to support that game, so you may want to do some amount of offloading to the cloud for to make sure your experience is rich. Okay, so let's look at this one. In the simplified model discussed, what does the local edge or cloudlet aim to provide? Is it A, large scale data center, B, a centralized computing resource, C, a micro data center at the edge, or D, a network router? Micro data center. Any other responses? Amit Sharma says C. Any other responses? Okay, yes. So the answer is C. It aims to provide a micro data center at the edge. It does not aim to provide a large scale data center because you cannot have that at the edge, and the edge is distributed, so it does not exactly aim to provide a centralized computing resource. A network router, not exactly, because you may need multiple of them. So what term is used to describe the simplified model containing the IoT layer, edge layer, local edge or cloudlet? Is it multi-layer offloading, hierarchical offloading, one level offloading, or centralized offloading? 1QC, what does that mean? Oh, question 1C. Okay, okay. Yeah, 1QC. Okay. Hierarchical, simplified model, right? So remember there was a one level, very simplified model. So the answer to this question is the one level offloading system. So in the so in the LSTM part, sorry, uh, so in the LSTM deep reinforcement task offloading context, what is the predictive offloading algorithm aim to improve? Is speed of computation, energy accuracy and convergence accuracy, energy efficiency or server security? No. If you look at the lecture, yes. So there was a hierarchical offloading system. Wait. Uh, so anyway, I don't remember. I don't think it's written in the slides over here, but Sir had explicitly mentioned about the one level offloading, uh, but the one level offloading system in which there was just the IoT edge. So in which there was just the IoT edge, there was a cloudlet, uh, and there was just the IoT layer, the edge layer, and the cloudlet. Right? It was called the one level offloading system. So I mean you can probably call it the one level because um, like the IoT layer is only like offloading to the edge layer, like that only like IoT layer then edge layer, right? So that way you could like call it the one layer, a one level thing. The like IoT layer is here. If let's say like the IoT like if let's say the IoT layer is like over here like on the bottom, and then on top of that there is like the edge layer, so that would be like this one level. Like this is the IoT layer, and then this is the edge layer. Like it's just like one level, right? So that is why it is like the one level offloading system. Is there in the slide? Okay, okay. I'm sorry, I couldn't find it, but you can check it. So what is the purpose of including multiple edge nodes in the model as explained? So one is A, to increase the complexity of the edge cloud system. B, to reduce the number of offloading scenarios. C, to distribute the computation tasks and reduce latency. Let's just do this quickly and then I'll just go to the next one. And or D, to prioritize communication over computation. So the answer definitely is C. If you have multiple edge nodes in the model, you'll be able to distribute the computation task and you'll be able to reduce the latency. Okay, so anyway, I don't know if we discussed this. Okay, so what is the predictive floating algorithm aim to improve? Speed of computation, accuracy, convergence accuracy, energy efficiency, or server security. So it is B's, accuracy and convergence accuracy. Let's go to the next one. What is the goal of task offloading in a multi-edge, multi-device computing scenario? Is it A, maximizing latency, minimizing energy consumption, C, increasing server loads, or D, reducing prediction accuracy? Goal of task offloading in a multi-edge, multi-device computing scenario. So yes, Amit Sharma says B. Any other options? Yes, so B is the correct answer. But what you might remember is we also want to minimize the latency also simultaneously. So that is not there in the options. But if this was minimizing latency, then A would also be the correct answer. Okay. So but over here we don't want to maximize latency at all. The latency is not really a good thing. Yeah. Right. Min. So the answer is B, minimizing energy consumption. So increasing server loads, reducing prediction accuracy, these are negative things, so we don't want to go there. So how is task offloading problem typically modeled? Is it A, as a linear optimization problem, B, as a deterministic problem, C, as a nonlinear optimization problem, or D, as a probabilistic problem? responses? Okay, so it's modeled as a non-linear optimization problem. So okay, it's not a uh, as was discussed in the notes. Let's take a look from what you remember. So over here, it's computation offloading in a multi-edge multi-device computing scenario is modeled as a non-linear optimization problem. Okay. What is the primary aim of dynamically allocating uh, resources in a task offloading? Right? Is it A, maximizing latency, B, reducing service quality, C, minimizing long-term cost, or D, increasing energy consumption? Yes. Any other responses? Min? Okay, so the answer is C, minimizing long-term cost. That is correct. Others are not relevant. So in a multi-edge, multi-device computing scenario, what is combined in the decision model to allocate resources dynamically? Is it A, prediction and server loads, B, prediction and task decisions, C, task decision server security, or D, task characteristics and latency? Prediction and server loads?
B. B.
B?
Hmm.
Yeah, okay, okay. Any other responses? Yeah, so B is the correct answer. Prediction and task decisions. So these two are combined in order to allocate resources dynamically. So the server loads, it is not exactly. I mean, it's not really relevant to the exact model. But okay, let's take a look at your notes. Okay. So so now we do some amount of prediction of the tasks and the edge server loads, right? So now that is kind of encapsulated in the prediction part of things, right? So but after that, in addition to the prediction, we use one more characteristic to figure out um we use one more characteristic to figure out what the optimal offloading decision would be, right? For example, let's look at there's a flow chart over here. See, so over here, what you remember was the LSTM. It kind of makes the decisions, right? And then after that, the decision model kind of makes an extra decision after that, right? So both of these kind of work together, and even if you look at this one, so there's predictive tasks information, there's then task information, there's also task decision. All of these lead to the final task processing step. Okay. So what are the two primary factors considered in minimizing the overhead of task offloading? Right? Is it A, network bandwidth and server security, B, network latency and energy consumption, C, server reliability and computational complexity, or D, task complexity and server offloading? Sorry. Okay, and before this, I actually want to show you one very good resource, right? If you want to understand this in more detail, there actually this lecture is actually based on a paper that was published in a journal. If you want, like much deeper understanding of. Yeah, so if you look at this paper, right, by yeah, so you will see a lot of these equations, right, that may have just been glossed over. They have been discussed in a decent amount of depth in this paper. Okay, so you can actually take a look at this entire paper if you want a much deeper idea of what was discussed in the lecture. So this is a very good resource. It's available publicly. I'm just putting it in the link in the description over here, in the chat box over here. So this lecture 13 was, it was largely based on this paper that was published. Okay. Fine. So for 13, there are no responses. Anyway, I'll just tell you the answer. Okay. 13 answer is B, network latency and energy consumption. Okay, so how is the task? Okay, no, let's take a look at this one. So, what is task flow rate in the context of task offloading? Just 1 second. Okay, wait. Let's go to the next. Just 1 second. Because we're at a shortage of time. I'm just looking for the most appropriate question. Okay, fine. So let's just look at question 4 maybe. Which techniques are commonly used in the online predictive offloading algorithm? Is it A, genetic algorithm and fuzzy logic, B, linear regression with decision trees, C, deep reinforcement learning and long short-term memory, or D, support vector machines? Yeah, so the answer is C. It's very simple. So how is the task offloading problem formulated in the discussed context? As a predictive task of loading or task offloading using deep reinforcement learning and support vector machines, as a joint decision making problem using LSTM and linear regression. Okay, or is it C, as a deterministic task offloading with fuzzy logic, as a predictive task offloading using DRL and deep reinforcement learning and LSTMs? Yes, the answer is D, that is correct. The other three are not relevant. So, what is the purpose of the training phase of the predictive task offloading offloading algorithm? Is it A, to predict characteristics of the next task, B, to allocate computational resources for tasks in advance, C, to predict the load of the edge server in real time using LSTM, or D, to improve the convergence accuracy and speed of deep reinforcement learning in the offloading process? See, the purpose of the training phase, right? Amit Sharma says D. Amit Sharma says D. Any other responses? Okay, yes. So the answer is D. It is the purpose of training phase of the predictive task offloading algorithm is to improve the convergence accuracy and speed of deep reinforcement learning in the offloading process. So yes, so let's take a look at your notes, right? So if you look at the training process, what happens is so basically the LSTM makes a prediction and this is sent to the reinforcement learning agent to in addition to this, the reward is sent to the reinforcement learning agent to make whatever would be the next prediction, right? And in the, you can say that the offloading decision phase is like the inferencing phase. So in that so in that also, like some sort of like similar processes is kind of happening. So okay, so basically in the end it is like the LSTM. See, from both these figures, like I don't want to go into too much depth right now, but we can kind of see in both these cases like the LSTM is kind of supporting the deep reinforcement learning agent to make whatever predictions it has to. Okay, so because of that you can kind of infer that because of that you can somewhat infer that predicting the load of the edge server in real time using LSTM would be like an insufficient answer. Okay, like because like the end goal is actually D. Like it may be doing this, right? But D is like the end goal. Fine. So what role does LSTM play in the testing phase of the predictive task offloading algorithm? Is it A, predicting the load of the edge server, B, predicting the characteristics of the next task, C, allocating computational resources for tasks, D, improving convergence accuracy? So, any responses? What does LSTM play? What role does the LSTM play in the testing phase of the predictive task offloading algorithm? Predicting the B. Okay. So is it C? Okay, B. Fine. So the allocation is not exactly being done by any of the models directly. The models actually just give their decision, and then the maybe the orchestrator or something like that will do the allocation. Okay. So so the answer is B. Predicts the characteristics of the next task. So how does the predictive task offloading algorithm? Sorry. So how does the predictive task offloading algorithm reduce response delay and improve the offloading process? Is it A, by predicting the load of the edge server in advance? B, by dynamically allocating computational resources? C, by minimizing task queue sizes? Or D, by increasing energy consumption? Dev has said A. Yeah, so the answer is 3A, by predicting the load of the edge server in advance. So, one second. So, what are the three components of the task model for a mobile device? Is it A, task task cache queue decision model, computational resources, size of task data, computational resource required to build maximum tolerance delay, time slots, edge server nodes, mobile device tasks, task queue, computation queue, transmission queue. Mm-hmm. Okay, so let's look at your notes for this one. So if you look at the task model, right? So it has size of the task data, it has the computational resource required per bit, and it has maximum tolerated delay of the task. So all these three are contained in the task model. That is why the answer is B. Okay. So anyway, I hope you didn't see the answer. What is the decision model determine for each new task generated by a gen- generated by a terminal device? So what is the decision model determine for each new task generated by a terminal device? Is Is it A, whether the task is executed locally or offloaded, the size of the task data, the energy consumption, or the transmission queue of the task? Any responses? What is the decision model determined for each new task generated by a device? Is it A, whether the task is executed locally or offloaded, the size of the task data, the energy consumption of the task, or the transmission queue of the task for the task? So A is the right answer. So the decision model does exactly that. It determines whether task will be offloaded or not. So what is the purpose of the predictive task prediction model based on LSTM? Is it A, to determine the decision and allocate the computing resources upfront, to log historical load sequence data, to train the deep reinforcement learning model, D, to maximize the total reward by making optimal actions? So I'm sorry over here. The LSTM does not exactly do the allocation of computing.
D.
D. Mm-hmm.
D.
D. Okay. I just want you to ignore this part. Allocate computing resources upfront for task. Okay. So yes. So D would be the right answer. Actually, A and D, if you ask me. Okay. So we want to. So the LSTM kind of makes a prediction, then that prediction is used by. Is kind of used by the deep reinforcement learning agent. So. Okay. So you could say A and D are. A and D are options. Okay. So what action does the decision model take if the error between the predicted task and the actual task is within a certain threshold? Is it A, add the task information to the training samples, B, follow the decision taken beforehand using the prediction model, put the new task information into the decision model, or D, discard the predicted task information?
Follow.
Any other responses? Okay, fine. So, what action does the decision model take if the error between the predicted task and the actual task is within a certain threshold? So, it follows the decision taken beforehand using the prediction model. Okay, so let's take a look at your slides. What happens? So if the error is within the threshold, then we follow the decision to offloading, right? And then we add the task information to the training samples. But if it is not, then we then we and then this new task information is also added to the decision model for making decisions. Okay, let's go to the 14, 15. Okay, so how does the deep reinforcement learning agent select actions during the training phase? Arey, I'm sorry, I'm very sorry about that. But anyway, I will. It's about the reasoning, right? So, how does the deep reinforcement learning agent select actions during the training phase? Is it A based on random selection, B based on LSTM predictions, C using an epsilon greedy strategy, or D using the Bellman equation? So it does. So during training phase, it does exploration exploitation, right? It tries to balance this out somehow with a certain probability. So how does it do this? How does the deep reinforcement learning agent select actions during the training phase? A based on random selection, based on LSTM predictions, based on an epsilon greedy strategy, or using the Bellman equation. So you can probably look at your notes for this. Does anyone have any responses? No? Okay, fine. So let's take a look at your notes. Fine. See, so the DRL training process involves selecting actions with a certain probability epsilon. So when a random action is selected, the size comparison between a random value sigma and the probability epsilon is used to determine whether it's a random action or a prediction action. Right? So, but how does it do this? So let's just I cannot find your. So anyway, so basically, like this strategy, right? It kind of falls under the epsilon greedy strategy, right? So with probability epsilon, it will determine whether it will take a random action or a predicted action. Okay. So that is the main idea of the epsilon greedy strategy. So this strategy is used to balance whether you're doing exploration or exploitation. Okay, it says over here. DRL typically uses epsilon greedy strategies for exploration and exploitation. Exploration involves random selection of any action with probability and expectation of a higher reward, while exploitation selects the action with the largest action estimate. So basically this strategy is relevant in the DRL training process.
What is action estimate? I didn't get it.
What is?
Action estimate, maximum action estimate. Yeah.
Where is it?
Just now you showed me. in the notes.
Okay.
Selects based on
Okay, see. So, so in this exploration exploitation, so what kind of happens is, see, like, how do I explain? So okay, so how do I give an example? Okay, so let's say you're in some kind of environment, right? And you already have like a decent like understanding of the environment, right? So you what you want to do is you kind of want to make a guess. You want to know what your next action will be. Okay, so now your next action that you take can either be based on like all the past actions that you have already taken, right? So for example, okay, I got the perfect example. So let's say you're going from here to some place, okay, and you know some very clear route already. So you can already you know some very clear route from point A to point B, but you don't. But there may be another route from point A to point B that may be a shortcut, but you don't know whether it's a shortcut or not. Okay, so when you
Actually, I got that. Actually, I was asking what is argmax, that
argmax. Okay.
what is maximum action estimate or some term is used. Select the action when it is in going for not random, means predicted action. Select the action with the
Huh. So
select the action with
select the action that maximizes the Q value, right? So that's what argmax does. See, you know the difference between max and argmax by any chance?
no.
Okay, so if you have okay, I'll just take out a simple. Let's take lecture. Okay, I'll just make some space here. So let's say I have a list over here. Okay. Okay. So I have a list over here. Okay. So can you see this thing? 1, 2, 3, 4, 5, 6. So over here, right? So the maximum value would. Okay. Let me just interchange these a little bit. So the max of this list, right, would be. So the max of this list would be 6, right? You agree with me? But let's say I have a function f of x, right? Sorry. A function f of x that takes an index, right, and then returns the element at that index. So for example, so let's say I take I say index 3, or let's say I take index 5. So at index 5, okay, if I give it index 5, it will give me this sixth element. It will give me this 6. Right. So now what argmax over here, argmax of f of x would be argmax with respect to x of f of x would be the value of x that will maximize this function f. So did you get this?
This f of x is the q value f of x.
Yes. So what is inside here is the action. Yes, f of x would be the q value. Yes. Okay.
X is the action and
yes.
Q value is the f of x.
Q value is the f of x. So if you go to the slides, right? So if you just take epsilon, if the model decides with probability epsilon that it will take the maximum, it will take that action which maximizes the utility. So it will choose that action AT that maximizes the Q, whatever.
Utility Q basically, that out here utility is Q.
Okay, did you get it?
Yeah, I got it.
Okay, fine. I'll just delete this. Okay, let's just go to lecture 14, I think. There's no time. Um, mm, okay, fine. So let's look at question 8. What does the term vertical offloading signify in the context of edge computing? So is it A, transferring tasks from edge nodes to IoT devices? B, transferring tasks from cloud data centers to edge nodes? C, transferring tasks between different cloud servers? Or D, transferring tasks between IoT devices and network edges? Okay, so the answer is B. Okay, so cloud to edge, and edge to cloud. This kind of transfer would kind of fall under the vertical offloading, and horizontal offloading would be within the same tier. So
Why not D? That is also IoT to edge, right?
IoT to edge. Wait just a second. I kind of lost the question.
Question 8.
Okay. Hmm. Okay, you could say D also, but does it say in the slides IoT device and network edge? Yeah, because they're not in the same tier, right? So you could say it is D also. Yeah, okay, fine. It's, between the IoT device and the network edge. Okay, fine. Devices access. Okay, fine. So yes, so the right answers um, would be would be cloud data center to edge or IoT devices and network edge. Both these B and D would be applicable.
Actually,
Yeah.
offloading, does it happen in downward direction? That is some other term. Offloading is always in upward direction.
Could call it downloading.
For downward direction, sir had used some other term.
I think
Download. So offloading is always upward direction.
That need not necessarily always
Not
be true, right? At least I have encountered it in multiple scenarios. Okay, I'll get back to you on this one. Okay. I sir did use the word downloading to go from up to down, definitely.
Yes. So use download
Yes.
from edge to IoT device. Download the results. He said right in the
Mm-hmm.
downloads the task results after processing.
Okay. So I have seen it used in, like, from what I remember, in some papers that I'll have to recall. Okay, so I just check a few papers and let you know if both these directions are valid or not. But like offloading, like, the thing is, we want to make sure that like what I have seen is offloading kind of implies that the burden of a device is kind of reducing.
Yeah. That is in one sense right.
Mm-hmm.
Basically, you can offload from one tier to another. Yeah.
Right.
But basically, when you are not short of resources, you can offload even to download lower tiers.
Mm-hmm. But yeah, I will just check this again. I have seen it used in, like, all kinds of scenarios. That's why. Okay, so what distinguishes horizontal offloading from vertical offloading in edge? Horizontal offloading involves transferring tasks between Azure nodes while vertical offloading involves transferring tasks between cloud and edge nodes. Uh, so horizontal offloading occurs between multiple edge nodes, while vertical offloading occurs between single edge node and the cloud. Horizontal offloading reduces latency by offloading tasks to the cloud, while vertical offloading improves efficiency by offloading tasks to multiple edge nodes. Horizontal offloading focuses on improving the capacity of edge nodes, while vertical offloading focuses on reducing the load on the cloud. Any responses?
Azure nodes, this can be any tier, right? For option A.
Hmm.
What does Azure node mean? It can be
Azure
edge node
just
also.
see Azure just Azure node was just like put in place because I just needed to create an option. But more precisely, Azure nodes you can say are cloud, right? Uh, like does Azure does have an edge and an IoT deployment also. Um, but yes, that is true. But it is not. It wouldn't. If you wanted to say A, it wouldn't be like most appropriate because it would mean many things.
D is the correct answer. A, if you take Azure as edge nodes or Azure as nodes in same tier, then A is also correct
Right.
because
Wait.
because the second part of the statement of A is also correct.
Right. I just want to check if check how Azure's edge nodes. So yes, so Azure does allow some amount of edge computing, multi-axis edge computing. Looks like it. So yes, I understand your point. So these Azure nodes could be either edge or cloud nodes. But the thing is, the definition of vertical and horizontal offloading is applicable even beyond Azure. So like so that is why like that would be a very specialized case. That was one part of my intention of including that in this question. That could be like one part of why this is there in the question.
But in the second part of D, why is it written between a single edge node and the cloud? Why is it written single? Like, is that word correct?
So like offloading can happen parallelly as well. Like, but like when you're offloading, like see, like when offloading happens, you get like the decision. It kind of goes to like one specific edge node, right? Even when like multiple edge nodes like offloading is happening, it is still like one task cannot belong to two edge nodes simultaneously. That's what I'm saying, like in the offloading process. Okay, so if that is clear, so yes, I understand your there may be some confusion because parallelly you can have offloading also happen. Like, parallelly multiple edge nodes may be offloading their tasks to the cloud, but at one time like one task that can belong to like one edge node before it's offloaded. After it's offloaded, you can say like half the task is here, half the task is there or something, but before it's like one at a time. Okay. Okay, let's look at lecture 15 now. Anyway, this is like you can figure it out. Which algorithm is specifically mentioned for recording the global snapshot? Is it Chandy Lamport, distributed snapshot, global communication, snapshot model? Just it's very easy. Okay, so the answer is A, Chandy-Lamport algorithm. So what is a snapshot according to the text? Is it A, a collection of people at one place, a picture taken by a photographer, a record of the global state, or D, a distributed environment? Yes. So Dev says it's a record of the global state. That is true. So Chandy-Lamport algorithm is used to take a snapshot, right, as we had discussed. What is the challenge in calculating a global snapshot in a in a in a distributed environment, right? So is it A, ensuring the consistency of the snapshot? So now this can have multi-correct. Ensuring the consistency of the snapshot, B, dealing with concurrent processes, C, managing communication channels, or D, handling processes running at different locations. One more thing. Okay, Dev says A. A. A and C. C is also, A is also correct. A is correct. Any other responses?
D.
D. Okay. So someone has said C. So we're not managing the communication channel exactly, right? So the only thing is communication channel should be active. Like we kind of want to make sure the contents of the we're kind of a lot more interested in the contents of the communication channel exactly. So yes, so A and D would be the right answer. Okay. So if there are various locations, then the clocks also may not be like fully synchronized. So you need to take care of all those things also. Okay, so let's take a look at this one. Which application in an IoT environment might require a global snapshot for functionality such as checkpointing and garbage collection? Right. So is it A, energy consumption, optimization, data encryption management, fault tolerance and system recovery, or D, device firmware updates? A, energy consumption optimization. So checkpointing, how is checkpointing linked to energy consumption?
Garbage collection can be related to energy consumption. You deallocate resources that are not being pointed to by any other resources.
Okay. Fine, that is one way of thinking about it. Okay. Okay, fine. So, checkpointing. So you don't need to store like various states, right? Like the way you would in a checkpoint when it comes to energy consumption optimization. So, anyway, I can see like if you're a computer science student, like when you think of garbage collection, you think of something like Java and and anyway, okay, I see. Okay, I see.
What is checkpointing?
So checkpointing it's kind of like, see, let's say you have an operating system, right? And let's say and you're afraid that it might, let's say, get corrupted or something. So you kind of save the state of the operating system somewhere. that is checkpointing.
Okay.
Or like even if you have code, right, we may want to save uh, various versions of the code. That's also like checkpointing. So answer is C, fault tolerance and system recovery. Mm, okay. One second. Uh, we do this one. Okay. Let's do this question. In the context of message passing between processes in a distributed system, what is denoted by Mij? Wait, let me just. The state of process Pi, the local state of process Pj, message sent from process Pi to process Pj, message received by process Pj from process Pi. Okay, this could be multi-correct also. Oh wait, just 1 second. 10th one. What is denoted by Mij? State of process Pi, local state of process Pj, message sent from process Pi to process Pj, message received by process Pj from process Pi. Okay, this is the last question. After this, I'll be ending the call. Okay, yes. So answer is C. Okay. So let's take a look at your notes as well. So if you look at so in Mij, the process is sent by process Pi to process Pj. Message Mij is sent by process Pi to process Pj. Okay, fine. Thank you. Thanks a lot for coming. Hope to see you. Yes. I will share the link. Sorry, last week I have not yet sent this. I sent both last week and this week's together, and it will be in the recording sheet that is sent. Okay. Okay, fine.